Welcome, everybody. My name is Robert Savage. I started a project called Pi4J about 2 years ago, this fall, and I am excited to be here today. This is my first DevOps, my first time in Belgium, and the beer's great. Very excited to be here, and we are going to talk about, we're going to divide the session kind of into two different focuses. The first thing we're going to talk about is the ability to use Pi4J. Sorry. Okay. Sorry, some technical difficulties why we started a little late. So we're going to start with a Pi4J overview and some introductory concepts. If you attended the talk yesterday, the university talk, then there's a good chance that there's going to be some, we're going to go over some of the same material, and that'll help reinforce it. And for the rest of us, I'm sorry? Okay. So we are going to first talk about Pi4J and then introduce you to how you use Pi4J, and kind of we'll do some code demos. We're going to do some demonstration. I'm sorry, guys. Is there a problem?
Why are you using
because I'm switching between 3 different devices.
Okay, but I don't get anything from you now. Okay.
Okay, sorry. When you're dealing with a lot of hardware and you're bringing lots of components across the Atlantic to Europe, there's some challenges. Power conversions, power supplies that only work on US 110, and then I've got my own HDMI switcher set up for all the different things I want to show you. So that just makes things extremely complicated, and we may have a few more glitches along the way. So we're going to do our Pi4J overview, kind of introduce you to what the project is. We're going to go through some code examples to show you how you can implement this on your own Raspberry Pis. And then we're going to switch focuses, and we're going to talk about smart devices and how we could potentially use Raspberry Pis and Pi4J to create smart devices, to create our own Internet of Things devices, kind of a DIY smart devices, because we're Java programmers. We're empowered to do this, and small embedded platforms like the Raspberry Pi help empower us to do these kind of goals. So we're going to talk about that, and then we're going to talk just a little bit on MQTT, kind of a communications protocol for aggregating multiple devices and endpoints together so you can aggregate data and make intelligent decisions across multiple platforms. So just before we get started, a quick show of hands as to who has Raspberry Pis. Who's purchased one? Okay, well, I'm talking to the right group then. Who's familiar with Pi4J? Okay, that's good. And who's actually coded and used Pi4J? Excellent. So you guys are probably already experts at this, but for the rest of the audience, we'll go through a little bit of introductory. What is Pi4J? So fundamentally, Pi4J is an open source project that was created specifically for the Raspberry Pi platform when the platform first came out, because the Raspberry Pi platform was created in university to help encourage the youth of Britain, and of course the world, to get engaged in the platform. Well, I thought that was an amazing idea. I really gravitated towards their concept. Myself, I started learning at a very young age, like in 1980, on programming. And what we had accessible to us were these kind of low-level devices. And I had Commodore computers, so when you turn the system on, you're staring at a prompt, and you have to start programming. So that's kind of where I got my start, so I could relate to the message behind the Raspberry Pi. But what I wanted to do was to make that experience accessible for 2 reasons. Accessible to Java programmers so that youth could also leverage the Raspberry Pi and our programming language, Java, to create projects that they could interact with their real-world devices and sensors. And then kind of on a personal reason I wanted to create it was so that I myself could create my own embedded devices and make my home smart. So that's kind of the reason why I created the project in the first place. So Pi4J is an open source project that provides Java programmers a low-level I/O access library. It's an object-oriented API because we as Java programmers prefer to model things kind of based on the real world, and we want to interact with objects rather than a utility kind of procedural type of implementation. And then I felt it was also extremely important to bring an event-based API to Java programmers, so that when we sense something in the I/O state of the Raspberry Pi, we can event that up, and you can handle it just in an event handler. And then Pi4J is built directly with Java code, so it's pure Java plus some C code for our JNI access to some of the low-level communications and memory of the Raspberry Pi. Now, you as consumers don't have to concern yourselves with the C in Java. We've kind of abstracted that for you, but just be aware that that's there. There is a native library that allows us to be optimized for that platform. So when we say low-level I/O interfaces, what do we really mean? Well, the Raspberry Pi has a number of different periphery devices, periphery access that it gives to us on a header pin. On that header pin, we can access its digital interfaces. Digital interfaces, GPIO, and pulse width modulation. So general purpose input-output and pulse width modulation. Digital interfaces just means that it's binary, it's on-off. We also have data interfaces, and that's where if you need to communicate with other chips, other hardware on your circuit, or perhaps a remote device via serial communication, there are data interfaces that we can access on the Pi, and Pi4J does provide access to all of these natively, as well as it also has some concepts for analog inputs. So if you need to measure voltage or measure some distance kind of thing, that might be an analog input. However, the Raspberry Pi hardware doesn't have any analog capability on it, so you have to include some additional analog conversion chips, aided DACs and analog to digital. You'd have to have these periphery devices connected, then you'd communicate to it through one of the data interfaces. But there are some analog capabilities in Pi4J, but just realize that that's an asterisk because you have to go through an intermediary piece of hardware. So GPIO. For those of you who aren't familiar with GPIO, we access GPIO on the header pins on the Raspberry Pi. So on our top diagram, we have, on the original version of the Pi, there was a 26-pin header. So those connectors you can connect wires to, and the ones denoted in yellow on the bottom graphic are the GPIO pins that you have access to. So GPIO pins can be represented in one of two states, high or low. Think on and off or 1 and 0. High and low electrically are represented by a positive 3.3 volts represents high, and 0 volts represents low. So that's the signaling, kind of how the GPIO pin works. That's the signaling layer, so that if you're outputting 3.3 volts on that GPIO pin, that it's high, and if you're outputting 0 volts, it's in a low state. There are different models of Raspberry Pis, including, I think as of Monday, we have a new A+ model. So there's the original A and B models, there's a B+ model, now an A+ model, and we also have the compute module, which is a embedded device that's in a DIMM form factor that you can directly embed into your own hardware. And it offers an impressive 46 GPIO pins for us. So the Raspberry Pi offers this hardware capability, and Pi4J helps us as Java programmers access that. And we can access all of the different models and the different GPIO configurations. So if we were to connect an oscilloscope to a GPIO pin, and we were to fluctuate that pin, let's just say we pulse it on and off, this is what the output would look like. As the signal goes high, the pin being 3.3 volts, we see that the square wave up here, we're in the high state, and then we drop to a low state. So this is electrically what pulsing a GPIO pin would look like, high, low, high, low. It's a square wave, just simple ons and offs. So if you want to wire your sensor or your device up to Raspberry Pi, you have to connect it to one of these GPIO pins. And I mentioned there are different models of Raspberry Pis that offer different pin configurations. So in your programming environment, you have to know what the pin address is that you're going to connect to. So if you go to pi4j.com and you select the model of your Raspberry Pi, you can see these graphics in larger detail and determine what pin address that you would need to configure for the very specific pin that you're going to connect to. So let's talk a little bit first about GPIO outputs. Outputs are the simpler of the two. Outputs are the ability for us as programmers to tell this GPIO pin to go high or go low. And what can we do with outputs? We can control things. We can control, we have a demo board here, and we can control, we have a strobe light, we have a signal bell, we've got a little LED ring around a button. And of course, things in our real world, we can control lighting and motors and power of different devices depending on the hardware configuration that you use. But just think that GPIO outputs are used to control things on/off. So if we look at a very simple GPIO circuit, we've got an LED connected directly to the Raspberry Pi's pin headers. The Raspberry Pi, as I mentioned, when we output 3.3 volts, it's high level. It's a fairly low voltage, so there's not a lot of circuitry or periphery devices that are going to operate at something that low power and low current. That the Raspberry Pi doesn't offer a lot of current on these pins. They're not really intended to drive your endpoint device. They're really intended to drive some other piece of a circuit or a relay or a solid state or a transistor to control other parts of your circuit, which then control the high voltage or high current. We'll look at that here, an example of that here in a minute. But an LED is a very low voltage, low current consuming device. So this is kind of the hello world of this hardware type of program that you might implement. So you've got your LED, and a red LED operates at 1.52 volts, somewhere in there. So we have to have a resistor to reduce the voltage and current to be acceptable for the LED. So with this circuit, we could, in our program, create a GPIO pin, an output pin. We could signal that output pin high, and that would, of course, turn our light on. We signal it low, it turns it off. Now, I was talking about the ability to control other devices, right? The LED's cool and all, and it's fun to see blinky little lights, but at the end of the day, I want to control real-world things. That's my goal. So we have a relay board. One more technical difficulty. Here we go. So we've got a relay board that we're going to connect to, and we have to provide power to the relay board for its circuitry to run. But then we're going to connect our two GPIO outputs, number 12 and 13 up there, and that's going to connect to input signals of this relay board. So when we signal those output pins high, it's going to trip this relay. And so with this very low voltage, low current, we can signal this relay board to activate one of the relays that's on board. And then we can use a higher voltage circuit on the back side of the relay. So when the relay switches, we'll close the circuit for the higher voltage circuit. And that's how we can control things. And that's how we're set up here in our demo board. And we'll run an example here in just a second. So first, let's take a look at what the code would look like. So these are Pi4J interfaces. You import the Pi4J libraries into your Java project. The first thing you have to do is you have to get reference to a controller. And we have a factory pattern that lets you get an instance of a GPIO controller. So the very first thing you do, you create yourself a GPIO controller. And then you can create input or output objects. Here we're creating a GPIO digital output object, and we've named it output. We use our controller to provision that output, meaning that we're going to, when we call this provisioning function, we're going to configure the hardware for that pin to know that it's a GPIO output, and we're going to configure other things like on an input pin we would configure listening threads and things like that to deal with eventing. But the provisioning allows us to basically reserve this pin for our usages and to configure it on the hardware. We do have to provide the address. We were talking a second ago about addressing. We do have to provide the address that we want to use for this pin, and then we can optionally tell it whether we want it to start when we instantiate this into a low or high state. Once we have our output object, we can now use simple methods, our object-oriented interface, we can use simple methods to signal it high or signal it low. Those are the primary two methods you'd use with an output object, but we do also have some utility functionality. We offer the ability to toggle the state, which would invert it from high to low. We can pulse it for a duration, meaning that you can say, I want this output to go high for 300 milliseconds. And that pulse can be a blocking or non-blocking call, depending on what your program needs. Not listed here, but we also have blink functionality. So if you wanted to tell something to just blink constantly, we have a function for that as well. So you can kind of see that we've created an object, we've provisioned that object with our controller, and now we can operate on that object. And that's all you have to do in your Java code, and now that's going to actually control hardware. So let's take a look at that now. We're going to switch over to, oops, not that one. Here we go. We are using NetBeans, and in the newer versions of NetBeans, it works great with the Raspberry Pi because you can configure the Raspberry Pi as a remote platform. So in earlier demos that I've done before I was able to make use of this, I would have to compile it. I would use Maven to compile it. I would SSH the output over to the Raspberry Pi itself, and then I would get on a console and start the program. But this is much easier because I can live remote debug and execute the program directly from the IDE. Now, it does take a few seconds to load over, so I'm going to go ahead and start it up, and then we'll take a look at the code. So I'm going to start example 1. So this is GPIO output. We have, in this example, we're going to do 2 outputs. We've got our GPIO controller. Then we have an output LED ring around this button at the bottom of this board. And we have an output strobe light. And momentarily it should start up, and it's going to turn those lights on. So we've got an output strobe we've set to high, and we've told our LED to blink. Additionally, we can set up shutdown options. This is optional if you want to, but it's a good idea to set up shutdown options so that if your program were to abnormally terminate or gracefully terminate, that the pins can be put back into a default state. So, very simple example. You can see that the strobe is illuminated, and there should be a blinking LED ring. I'm sure there is. I hear it. There we go. So that's all completed just through our programming. These few simple lines of code made that functionality work, which is pretty cool. Now, that in itself, okay, that's great. It's flashy, blinky lights. But if you extrapolate that into what we can do in the real world, we can now control things directly through our Java code. So let's go back and talk about inputs. GPIO inputs, they can be used to sense things. So we used outputs, and we would drive the state of the pin high or low, which in turn we could control things. For GPIO inputs, we want to listen to the state of the GPIO pin. So we're going to have other circuitry that's driving the high or low states of the GPIO pin, and we're going to monitor those in our Java code. We want to be aware when something changes. So GPIO inputs provide us that capability. And on the diagram, or the illustration here, you can see there's all kinds of different things we could connect to it. Door sensors. On our demo board, we have a water level sensor. We've got an IR beam break sensor, which is an infrared beam that comes across and is reflected back. And if you interrupt that beam, it will signal with our circuit, it will signal our GPIO pins. So all kinds of devices you can connect if that device just provides a simple on-off kind of capability. So if we look at the simplest example, kind of like our Hello World, our LED example, for inputs, the simplest example would be a momentary switch. So we are sourcing the momentary switch with the 3.3 volt output provided on the Raspberry Pi, and we return that into our GPIO pin. So when we depress this button, we close the circuit, allowing the 3.3 volts to come into the GPIO pin, thus signaling high. And when we release the switch, of course, it reverts back to low. Now, GPIO inputs do require an input reference. So it's important to note that a GPIO pin, when you configure it as an input, it doesn't know if it needs to be high or low at rest. It doesn't know what kind of circuit you're creating. So we have to give it some kind of a reference voltage so that it knows, in the absence of our circuit doing something, that it needs to be biased to either a ground, a 0 volt, or 3.3 volt high signal. So fortunately, the Raspberry Pi includes on board, on the hardware, internal pull-up and pull-down resistors. And we can configure that when we provision our input pins. We can configure it to be either pull up or pull down. So what I mean by pull up or pull down, if you are creating a circuit like our momentary switch just a second ago that's going to provide a high signal to the GPIO input pin, then we need to give the circuit a bias of a pull down resistance to pull it down to a low signal. And conversely, if you were going to create a circuit that provided a ground, provided 0 volts to signal your GPIO pin, then you would need to configure it as pull up so that in the absence of your circuit, it binds to a high state. Now, we can certainly use the Pi4J and Raspberry Pi onboard pull up and pull down resistors, or if you choose to, you can create this directly in your hardware circuit. For the purposes of our hobbyist and demo uses, we'll just use the ones that are built in, but it's important to note that there are some cases where you may actually want to build that onto your circuit. Many cases, especially if you're going into production. So a GPIO, so this is what's going to look like for our Pi4J interfaces. We've got our controller that we already created. Now we're going to provision an input pin. When we provision that input pin, of course, we provide the address of the pin that we want. And then we give it either a pull up or pull down resistance. We can tell it here as to which one we want to use internally. So we talked about event-oriented APIs earlier. Here is where we care as Java programmers about the input for a GPIO pin. We can add a listener to our input object, and because we now have Java 8 accessibility on the Pi, we can use a Lambda expression to have very simple, clean code. And in this example, we're going to take the input, the change that came into our input, and we're going to set the output state to match. So effectively, if a high signal comes in, we're going to tell the output to also go high. And then if we return to low, we'll get an event, and we'll tell the output to go low. So very simple concepts, but let's just go ahead and take a look at that in code. We've got, and I'll get started. Make sure it's running. There we go. So while that's loading up, we'll kind of talk through the code a little bit. So we have our GPIO controller we've already created. We've got our two output LEDs that we created in the previous example, but now we've also got an input pin. And we are provisioning that input pin, and then we come down and we add ourselves a listener. And in this example, we are going to print the change state of that input pin out to the console, as well as we're going to tell both the output LED and the strobe light to match the state, so to turn on. So as we depress the button, it will turn on, and release the button, it'll turn off. So I know these aren't really exciting demos, but you can kind of get the idea that this is how you have to extrapolate what you can do with this capability, and we'll go into some additional demos later. So when I depress the button, both the LED ring comes on and the strobe light gets turned on, and then when I release the button, it goes back off. It's not rocket science, but with these tools, and when you're armed with this capability, there's a lot of things that you're able to do. So next, we're going to talk about components. So GPIO inputs and outputs are great, but that doesn't necessarily mean I want to create a program with business logic around the concepts of GPIO. GPIO is highly tied to our circuit design. I have to know what high and low means. High doesn't necessarily mean on. High could mean low, depending on your circuit. Fix this one more time. So in Pi4J, we also have a component library that allows you to use this abstraction layer to use components rather than raw GPIO and inputs and output objects. You still create the inputs and outputs, but then you can feed that into a component, and then you can use the component throughout the rest of your code. And then these components provide interfaces that are more real world. So we have things like a light component that has an on and an off, rather than a high or low, because high or low doesn't mean anything to me because I'm a light. On and off means something to me. And should your circuit design ever change, your changes would be, your program is insulated from that change because where you configure those GPIO inputs are isolated to some initialization portion of your program. So components, the components that we have available is this list above, and it's continuously growing. And if you have a need for other components, obviously let us know. If you're able to contribute some to the project, that's even better. So here's what a light component would look like. So we have our output that we've already defined previously, but now we're going to create a light object with the light interface, and we're going to give it a concrete class, instantiate it with our GPIO light component class. Oops, thanks. So I've got a little HDMI switcher up here, but apparently it doesn't stay in sync. It worked great yesterday, but today not so much. Okay, so here's our light component, our light interface, and our GPIO light component that is our concrete implementation using GPIO, and we provide our output as the constructor argument. Now that we've got our light, like we mentioned earlier, you can execute these simple functions against it: on, off, is on, is off. So it's more notionally, in your program, it's going to read more like a real-world scenario. In our next example, we've got a momentary switch. So this is an example of a component that we'd use for an input. So a momentary switch, we instantiate using our input pin, and then and here's where we can tell it what high and low mean. In this example, we're showing that high means on and low means off, but I could easily reverse those depending on my circuit design. And then throughout my program, I can still use on and off and it'll work. I don't have to care what high and low mean. So that's the benefit of using GPIO components. So we're going to switch to the components demo. And functionally, this isn't going to be anything different than what we just saw. The difference would be that in code, we've created all of our inputs and outputs that we previously created, but now we're going to create our components around those GPIO objects. So we've got a momentary switch for our button on our demo board. We've got a light component for our strobe light, and we've got an LED component for the little LED ring around the button. So instead of the listeners that we created directly on the GPIO pins, now we're going to create listeners against our components. So in the case of our button, which is a switch, momentary switch component, we're going to add a listener, which is a switch listener interface. Again, we're using a lambda expression, and now in our program we can simply say, hey, if the switch is on, then turn the light on and turn the LED on, else turn it off. So you can kind of see that it reads a little bit better in terms of what you're trying to accomplish, rather than someone coming through and having to understand the circuit design or understand the lower level details of the hardware. Additionally, you can create listeners on the other, even on the output objects like the light. So perhaps if the light comes on, I also want something else to occur. So I could create a listener on the output change state and then implement whatever business logic I want. Here I'm just outputting the information to the console. So the program has started. I'll leave the console up, and we are going to, well, I said I was going to leave it up, but it went down again. All right. There we go. Okay, so our program's up, and again, it's functionally going to work just the same, but using components and component listeners. When I press the button, the strobe light should come on, and the LED ring will come on. So that's what we end up with, and when we release, it turns off. So really no different. You can see it's the same outcome, but using different interfaces and different classes so that you insulate your code from changes. Okay, so that kind of concludes the portion that's just an introduction to Pi4J and how you would use GPIO, how you signal these pins and what they can potentially do for you. Drive outputs to control things, listen to inputs to sense things. But what can I use all of this for? Because what I want to create is a smart home, smart devices for a home. So we all know what smart devices are and the Internet of Things, the big buzzword these days. But let's break it down just a few simple things of what we recognize as a smart device. Well, first and foremost, it has to be connected. We've got to have some kind of internet access or network capability to work with this device. More than likely, it's going to have some kind of autonomous behavior associated with it too, so then the absence of human interaction, it's going to provide some functionality for us. And lastly, it should provide some kind of interactive capability. Maybe it's going to notify us, it's going to tweet us, it's going to send us an SMS for some alert condition, or maybe we want to use a mobile app on our phone to control some device. So I think these are kind of just, if we break it down to the very high level, I think this is what represents a smart device. So now we're going to talk about what we could potentially do with these things. We want to create smart devices. My wife and I just recently moved into a new home, and I want to create a smart home. So this is my goal, and I'm going to work on this over the next few months to create a series of projects to automate my house with smart devices. Now, I could look for off-the-shelf solutions. There are some great solutions out there. There's awesome Nest controllers. There's a new Lana project coming out for controlling sprinklers. But the problem with these devices, in my perspective, is that it's all proprietary hardware. Oftentimes, it's proprietary software and apps, and they're independent apps for each thing that you want to do. So if I want to work with my HVAC and change the temperature, I've got to go to that app. But if I want to control lights, I've got to go to a separate app. And then those apps don't talk to each other, and I can't do intelligent things with those devices. I can't say, if the security system's on, also make sure that that my lights get turned on or off. So I can't make intelligent decisions when all of these different proprietary devices don't intercommunicate. There's no interconnectivity or interoperability between them. So I think that's what's missing from our current off-the-shelf solutions. So what I want to do is create do-it-yourself smart devices using Raspberry Pi, Java, and Pi4J. So we can do that in a couple of ways. We can implement our own sensors directly. So we have examples of that with our water level sensor. We could sense flood conditions. We could, we've got our IR beam brake sensor. We can sense some kind of proximity or trespass kind of scenario. So we can use raw sensors, or we can also find potentially dumb devices that are already out there that perform nice encapsulated functionality, but we want to augment their functionality and make them connected. So I think there's two kind of plays that we can take and create smart devices in a do-it-yourself way. So we're going to go through several different scenarios, and these are personal scenarios that I'm going to implement in my home. So first of all, I've got a basement, and that basements in the U.S. can, I don't know how it is here, but they can take in water, and oftentimes you have a sump pump, which is a pump that activates when there's water and it pumps water out, so you don't gather a lot of water and get flooding in your basement. But sometimes those pumps fail, and it sure would be nice if I had some kind of sensor to let me know that the water has reached a level that's now a concern. So I want to implement some form of a water level sensor to let me know if my basement's flooding. And then now that I know the basement's flooding, now I can do some fun stuff. I can SMS myself, because I sure need to know, right? I could activate some kind of signal, some audible or visual signal. I could use that information perhaps to turn off electrical equipment that might be in the basement, to shut it down, to make sure that if there is a flood condition, that it's not going to come damage other equipment or create an extremely unsafe condition. And then finally, I want to use mobile devices and maybe a whole home dashboard kind of thing to monitor the state of my home, so I can see these conditions kind of in a one view perspective. HVAC systems. So HVAC systems, when the air conditioning's running, they collect condensate water. When they're working properly, they dispose of that condensate water through safe sewage systems. However, oftentimes, in the States, we have HVAC systems that are installed in attics, which is a very dirty place. Insulation, insects, things like that get into the pipes and clog that condensate drain. When that happens, the condensate overflows and goes into a catch basin. So there's an overflow catch basin beneath the HVAC unit. But that's an alarming case, because if the water gets too high and it's not properly draining from the overflow bin, then what's going to happen is it's going to come out onto your sheetrock and come through the ceiling. And usually the way we get notified is that the ceiling starts peeling and water starts coming down. And that's not the best time to be aware of that, especially if you're not at home. So there are existing devices on the market, like this wet switch, that you can connect directly to your HVAC system. And what it's designed to do, it's a moisture sensor. So when it senses moisture in your catch basin, it will shut off the HVAC system, which is great. That in itself is an awesome piece of functionality. But it sure would be nice if I knew that it did that, other than the house heating up and me finding out about it 20 hours later. So what I want to do is augment that device. It has wires on it that will allow me to read the state of it, so I'll know if it's in a trip state. So I can wire that into my GPIO, and now I have knowledge about what state that's in. So I can send myself notifications. I could shut down equipment. I could raise sirens, and then I can include that information on my whole home dashboard. I'm pretty lazy, so I would really like to know when the mail comes, because I've got a long walk to get to the mailbox, and oftentimes I go there. It's probably healthy that I actually walk there several times. I work from home, so I don't get out that much. But it would sure be helpful if I knew when the mail came. So what I'm doing is implementing a magnetic door sensor inside of a mailbox, and so I know when the mail has come. So when they open and close that, I'll get sensed input into the Raspberry Pi, and then I can send myself an alert. I could ring a bell so that I'm notified while I'm in the house. There's different things I can do once I have that information. Driveway alarm. So, like I said, our driveway is kind of a distance away from our house, and our house is pretty open. It's got a lot of windows. And when couriers or people come up to the home, we're not always aware of it. So usually sometimes the first time we get notified, they pull up in our driveway, and here we are sitting at the kitchen table, sometimes dressed, sometimes not, and there are people right outside our window. So we would love to know if there are people coming up the driveway. So we're going to use our IR beam brake sensor. We're going to install this at the end of the driveway and know when some vehicle travels up the driveway. Be notified audibly and via our SMS if we want. Now, maybe if the security system's on, maybe I'd also like to take some photos of who's coming up my driveway. Maybe I want to take motion video. So once I have the knowledge, then I can perform this other intelligence. Garage door opener. This has been one I've been wanting to work on for a long time, so I wouldn't be shocked if this is the first one I do. But on the garage door opener, we often forget to shut it. I sure would love for it to send me a reminder to say, hey, I've been open for 15 minutes. Do you want to shut me? So I'm going to use relays and magnetic door sensors to understand the state of the garage, and then relays to drive the garage door opener closed and open. So once I know the state of the door, then I can actuate the garage door to, change states. So again, I would like to implement some intelligence against the garage door to say after an elapsed period of time, let's send a notification. Maybe if I don't get a response from the user after an additional elapsed amount of time, maybe I'll automatically shut the door. So there are things like that that I want to implement around the garage door. And I want to be able to access my smartphone to open and close it as well. Maybe I've got maintenance personnel come into the house to fix something. I just open the garage door for them once they get there. Sprinkler systems. So sprinkler systems may require a little bit more sophisticated circuitry or a higher level communication protocol, either over the network or via serial, but I also want to have sprinkler systems. My wife has a garden, loves to keep it watered. She leaves town, I don't water it, things die. There's big problems at our house. So I need to automate that so it's not my fault anymore. Maybe I want to be aware if it has rained, so I need some kind of a rain sensor so that I'm not wasting water. And perhaps I even want to add the intelligence to go out and check the weather and say if it rains in the forecast, if there's a certain percentage chance of rain, let's go ahead and skip watering because more than likely I don't need to. And then be able to control and configure and schedule that from my smartphone, which would be awesome. Security system. I'd love to be able to control my security system, check the state of my security system when I'm away. Maybe, again, I'm a very forgetful person, therefore I often forget to set the security system, and I would love to be able to set it remotely. But I think more importantly than that, I think it would be useful information in my smart home to understand the state of the security system. So if the security system is armed, maybe there's other behavior that I want my house to perform. If the security system's armed and somebody crosses my driveway through my driveway sensor, maybe I want all the lights in the house to come up. That might be a good scenario. HVAC systems. So I would love to augment our HVAC system so that I could remotely control and sense the temperature. Sense the temperature in different rooms, compare that with the outdoor temperature and, make intelligent decisions about running the HVAC system. But maybe even more than control, I'd like to just monitor the state. I'd like to know when the compressor's running, how long the fan's running. Maybe I can make some analysis over time once I've gathered some data to understand the usage patterns, and maybe I can optimize and save money. So things I want to do with the HVAC systems as well. So today for our demo, obviously we can't build all of that. Those are big lofty goals and dreams that I plan on implementing. But for our demo today, why don't we just break it down to some, let's build a proof of concept. So let's just take some of the simpler ones that we can do with GPIO and implement our driveway alert, a flood alert for our basement, a mailbox notification when mail arrives, and an alert if the HVAC system has a problem. So we're going to use our Raspberry Pi and Pi4J to create this system. So why don't we switch to that? And I'll get that loaded, and we will take a look at the source code. This is a JavaFX app because, again, we want a smart home kind of dashboard. So we're going to use JavaFX running directly on the Pi, launched from our NetBeans application, and we're going to kind of display the state of these sensors on screen so you can kind of see the interaction and see them working. So we have a JavaFX, our main class simply just loads the FXML, and then our FXML has a controller an initializable interface so that we can, when the FXML layout comes up, our controller gets instantiated and we can initialize all of the GPIO functionality. So here you see again, we've got our GPIO controller, our GPIO input and output pins, and we are also going to create sensors for our driveway sensor. And then here's our sensor listener implementation. So all of our business logic, the functionality that we're going to do in our demo today, is all implemented in these listeners. And we've got our flood sensor here. And finally, our HVAC, our HVAC link sensor, and then there's a mailbox sensor down here. So these are just very simple circuits, and they're just simple inputs to our system. But once we know this information, now we can use our own business logic to perform our smart functionality. So once that is loaded, it says it's running. Let's see. Will the demo gods be kind today? There we go. So this is our home dashboard, just mocked up for our demo today. And what we're going to do is I'm going to come around to the front of here, and we're going to interact with some of our devices. So we wanted to be aware if we had a flood condition. So if water were to rise in our sump pump area in the basement, this little float's going to lift up, and there's a magnetic reed in there that's, when we lift the float, which contains the magnet, it's going to trip the sensor inside it and complete our circuit, therefore signaling high our GPIO pin. So when I raise this, we should get an alert. There, so we've got our flood alert, which on screen, you can see it up here. And when I release that, we also go ahead and do a visual notification, and when I release it, the flood condition's gone. So you can see that here we are just interacting with hardware and driving our JavaFX application. So next we have our driveway sensor. We'll do that one next. So if someone were to pull up into the driveway and break the beam, I get my driveway activated alert. So now I can, here I'm just showing it on screen, but you can imagine I could send SMSs or do something more intelligent with it. The post office is coming by. They're going to drop my mailbox off, drop mail at my mailbox, so I've got that alert. And then finally, I've got my HVAC system. So this is the device that we had that will that has its own built-in functionality. All of these others are raw sensors that we're using to create functionality. This one is embedded, but it does have some test buttons so that we can kind of emulate the behavior. So we're going to go ahead and we're going to push to test it, and then we get our HVAC alert on screen, and then we can reset it. So you can see very simply, we're just using GPIO inputs. We're sensing these things directly from hardware, and we're controlling our logic, our program logic in Java. So it's pretty cool. Let me switch back. So that was great. We created a demo. We've kind of done our proof of concept that we can get the hardware working. We can sense this information in Java. We can write our own Java business logic for whatever it is that our goals are for our project. But you think, hey Robert, you mentioned smart devices. What about connectivity? We didn't do anything connected. All we did was had one Raspberry Pi with GPIO talking to these devices. But in a real world scenario, I talked about a variety of different locations. I talked about a basement, garage, mailbox way out there, attic where the HVAC system is. So more than likely, we're going to have distributed systems throughout our home. Maybe multiple Raspberry Pis running, these programs independently. So we need a way to aggregate all this monitored and sensed data. We need to share information between sensors, because if we're going to perform any kind of intelligence functionality, we've got to share information between these devices. So how would we want to share information and access and control these devices throughout our home? Well, one option would be to use MQTT. So that's what we're going to kind of demo that here today. So MQTT, we'll go into a little bit more depth here in a second, but it's a publish, subscribe kind of client-server model where all of our independent devices can report their information, publish their information, their sensor information, up to an MQTT broker. So our MQTT broker acts as that kind of central knowledge, that storage of information, and then anything that's interested in being a subscriber to that information can collect those sensor states from the MQTT broker. So we had all our sensors on the previous slide publishing data in, but now I have my Android client on my tablet, I've got my mobile phone, I've got a web, perhaps I'm going to do something with a web server to create a web dashboard, or maybe a thick app on my desktop PC. So I want to be able to use the information that's available, that's been collected, and then display that information on a console or make intelligent decisions about that data. Or perhaps these endpoint devices would initiate MQTT messages to control devices if we were going to control something. So we're going to use MQTT as kind of our central communication platform. So those of you not familiar with MQTT, it's message queuing telemetry transport. I can't say that very fast, but that's what it is, MQTT. It was originally developed. It's not new. It's been around for a long time, but it's a machine-to-machine connectivity protocol. It was designed to be an extremely lightweight communications protocol with a very small code footprint so that it could be deployed on embedded devices. And by Raspberry Pi standards, it's a pretty capable embedded device versus some of the embedded devices we've worked with for years. So the small code footprint's important for embedded devices, and it's an open standards-based protocol. So there are multiple implementations of it that all conform to the same standards, and they're interoperable. MQTT supports asynchronous messaging, which is important for us in our connected home scenario, because all of these sensors are operating independently and without direct synchronous communication. So we need all of that information to come in asynchronously, and we'll gather it together. So the MQTT is not just something I pulled out of the dark ages. It's an emerging protocol competing to be an IoT standard. So there's lots of buzz around. I'm sure there's other sessions and topics here at the show to talk about MQTT, but it's one of the the leading ones that's going to be a standard for IoT type of implementations. There's a few others, so it's probably worth evaluating the leading ones for your particular project's needs. The reason I chose MQTT, because it's a simple publish-subscribe messaging protocol, so I can publish messages from the sensors and then subscribe to that topic. They're called topics when you publish a topic. I can subscribe to those topics to receive the data back. MQTT also offers a last will and testament, which means that if a device were to fall offline, that there can be a default kind of message or default information in the topic that it will revert to when that client gets disconnected. There's quality of service, which can provide guaranteed messaging, guaranteed to all, guaranteed to one, fire and forget. There's different levels of quality of service that you can provide when you publish a message. And then one of the important things for me is message persistence. Because if I'm going to build a dashboard, I don't want to wait around for the sensor to report its next reading. I need to know the last state of the sensor, because when a UI comes up, I want to be a very responsive UI, so I need to know state. So for me, in my usage, message persistence is important because I can just read the last message that was given to receive state. And finally, MQTT supports binary data inside of its payload, so I can put anything in there I want. In our demo, I'm just packaging some JSON in there, but I can imagine other scenarios where I may have a more complex piece of data, maybe an image or something that I want to share around. So it supports binary payloads. It is TCP-based, and we can protect that layer through security with SSL, TLS implementations. There we go. So we're not going to go into depth here, but we talked a little bit about publish, subscribe. In this example, we've got client A, who's going to be a publisher. Client C and B are going to subscribe to the broker for a particular topic. So in our demo here, we're just using one topic, but in the real world, you'd probably have a topic for each sensor, and you report information about that sensor through that one topic. So in this case, they're going to subscribe to the temperature topic. So if you look at the right pane, client A is now going to publish a new temperature reading to the temperature topic. The broker is going to push that temperature reading out to its subscribers. Client C and client B is going to push that information out. So I think we all know what publish subscribe means, but that's effectively what it's doing. So for our demo today, we are going to use the following softwares. We've got Mosquito, which is going to be our broker, effectively server. So, it looks like I put the wrong URL there. So ignore that first URL. Mosquito is the broker we're using. In the Eclipse project, we're using the Paho library. They have a Java implementation of a MQTT client. So we're using that directly on the Raspberry Pi to be the client to our broker. And finally, we have MQTT FX. If we want to from a diagnostics perspective, if we want to kind of sniff the wire, see what's going on, or also observe the topic for programming and diagnostics purposes, we can use MQTT FX, which is a Java FX application, to view and inspect the messages. So let's take a look at our MQTT. So we're going to load up the MQTT demo. And I moved the implementation logic from the Java FX controller in this example because I've got two different mains that I'm going to run. One for running directly on the Raspberry Pi, and then one that I'm going to run on the desktop. So I've moved the implementation around, but we will get the Raspberry Pi one started, and we'll take a look. So in this main, I went ahead and moved the GPIO logic to main so that I could start this independently of the Java FX app. Because what I'm going to do here in this example is use the same Java FX program both for the Raspberry Pi, but as well as my desktop. So the implementation for our GPIO logic is implemented here in the main that I'm going to run directly on the Raspberry Pi, and I'm going to publish the sensor information to a topic on an MQTT broker. I have Mosquito running here locally, so my MQTT broker is just here on my desktop. You can certainly use at iot.eclipse.org, you can use, they have a sandbox one if you want to play with theirs. It certainly works well over the internet, or you can run your own MQTT broker. So our demo says it's up and running. Let's see if we can switch to it. There we go. So now our Raspberry Pi is running the Pi4J logic to monitor the equipment, but it's also running an MQTT client to publish that information to our broker. So let's just make sure we're working. So if I trip a sensor, we're getting our messaging. But what I can do now is, because now we're MQTT, we're not just localized to that Raspberry Pi anymore. I can now run the same Java FX here on my local desktop. Oops. I've got to open it first. Here we go. I'm going to launch that. So now I'm going to switch to my local desktop, and you can see here we're running on the Mac, and it should have the same sensor information. So if I trip a sensor, now we see it happening on the desktop almost instantaneously. So we'll trip the flood sensor and our HVAC sensor. Great. So we've used MQTT to publish that information over to our broker, and now our broker is sharing that with the subscribers. So I've got a subscriber running directly on the Raspberry Pi and on my desktop. But that's not enough. I want to run our subscriber on my mobile device so that I can also get this information on mobile. So I've got an Android client here. I've got a tablet. And let me switch to the tablet. Here we go. So I just created the same, almost the same Java code, different, obviously it wasn't Java FX, it was Android, but I've used the same MQTT implementation on my Android client, and when I trip sensors, I also get the messages here. So, it's just a demo to show that you can use Pi4J, Raspberry Pi, and these advanced concepts like MQTT to now get this information, the sensor information, shared around the environment. So that's kind of the goal for my MQTT implementation, to create these smart devices and interconnect this information and then make use of that intelligent information throughout the home. So my personal goals for 2015 is to start creating these DIY smart device projects using Raspberry Pi. I will blog about them on my blog, savagehomeautomation.com. Every project will include all of the hardware parts list, include the wiring schematics, and kind of the instructions and source code. So it'll be fully open source, do-it-yourself smart devices. So that's our goal, because I want to build this for my house, but maybe you guys can get some use out of it too, or modify it to meet your own needs. But I want to create these smart devices so that my smart home has this intelligence, and I can fully achieve my dream of being lazier and having, Pi4J and Java code do everything for me. So with that, I want to thank you guys for coming, and I will go ahead and open it up. We've got a few minutes left for questions. If you guys have any questions about the project, Pi4J. Any questions? Yes, sir. So the question was, what happens if your Raspberry Pi doesn't have enough GPIO pins? You have a need for a much greater capacity than whatever the Pi offers. So there's a couple of solutions. You'd mentioned, do we use multiple Pis? I think that's a decision as to whether it's practical for your implementation. If everything's local, it's in everything that you're wanting to sense is right there in one space, no, I don't think you would use multiple Pis. What you could use are GPIO expanders. Now, I didn't go to it here in the demo, but you can take a look online. Pi4J does support GPIO extenders, which allow you to connect through one of the data interfaces to expand your GPIO capability and give you access to more GPIO pins. So you can use that, and then in the Pi4J programming logic, it still looks like GPIO pins, but it's really going across a data interface to another periphery circuit board. So that's one option that you can do to expand your capability. Or look at the higher capacity models. The compute module supports 46 pins. So a little more expensive, but you have greater capacity. Anybody else? Well, thank you guys. I appreciate it. You were a great audience. And if you have any questions later, feel free to come up, or you can blog, or you can tweet me, or contact me via email. These are my websites. We have the project website, pi4j.com, my personal blog, which is savagehomeautomation.com, and the respective Twitter accounts. So thank you guys.